All right, so quick sort is nice in that it can't, most of the time it's in log in, but we can't guarantee in log in. And if you're using a real-time system, maybe the worst case in squared is not acceptable. We'll just say for some reason sorting is keeping a man's heart alive, right? Well, just extreme example. So and we'll just say for sake of argument, in squared is not acceptable. It needs to be in log in to keep everyone happy or keep them alive. So we need to have something that guarantees in log in, is what I'm trying to say. You okay, David?
Yeah.
Okay. All right. So another one is called merge sort. Merge sort guarantees in log in. And it's kind of, when you first think about merge sort, it's going to be a quick sort, but you're recursing in the opposite way. And that'll make sense in a moment. It's still a divide and conquer technique, but it first partitions the list into two lists. It doesn't pick a pivot. It just straight out partitions the list in two separate lists, flat out. Then it sorts the sublists and then combines the sublists into one sorted list. So it's different how it's partitioned. It doesn't have a pivot. It just flat out partitions them in two and then combines them together. I think the slides, I recall, have a really good picture of what this looks like. Beautiful. This is way better than what I could draw on board. The first step in merge sort is you divide everything out. Divide the list in half. So the lower left half, right half, divide again, left half, right half, until you have two elements, or one element. And again, safe assumption, an array of one element is sorted. So we're good there. Then what you do is you combine these sorted lists into one sorted list, or the two sorted sublists into one sorted list. Before I do that, does everyone see how it's being divided out? Just being broken apart into each little section? Perfect. So 35 and 28, all right, 28's lower, so it goes in first, and then that list is empty, so I'll put the 25 in. 18 and 45, 18 is lower, so that goes in first. The left list is empty, so we'll put the 45 in. 62 and 48, well, 48's lower, so we'll put that in first. That one's empty, so we'll put the 62 in. 30 and 38, well, 30's lower, put that in first. 38 comes afterwards. All right. Wasn't too helpful there about how that worked, but let's look at the elements of 2. How does this work? Let's evaluate the 28 and the 18. Which one is lower? The 18. So we put the 18 in, and now this list will only contain the 45. So you can compare the 45 and the 28. The 28's lower, so that goes in. Increment over. Now the 35 and the 45, you compare. 35 is lower, so it goes in. 45, of course, and then you're empty, so then the 45 goes at the end. Similarly over here, 48 is the lowest of this list, 30 is the lowest of that list. So you compare the two lowest, 30 is lower, so that goes in first. Increment your pointer over to 38, so you're comparing 38 and 48. 38 is lower than 48, so put 38 in. Now that this list is empty, you just copy everything over. Y'all see pictorially what's going on? I'm going to go write it up on the board just to make sure it's clear. What do we have? We have 18, 28, 35, 45, and then next comes 30, 38, 48, and 62. So we're going to say left position equals 0. Let me go bring this up on the board. Left position starts at 0, aka the 18, and then right position starts at 0. Okay. And your loop is going to continue until both of these position variables are after the array. All right. Key piece of information. The first element of the two arrays or lists is the lowest element. So if you're comparing the two lowest elements of the list, which one's ever lowest would be the lowest of the combined list. Does that make sense? All right. 18 is lowest here, 30 is lowest there. Which one's lower? 18. So we're going to start with 18. Then we're going to increment the left position by 1, 28. 30 and 28? 28. So we put the 28 here, and then we
Increment right position.
left position right. So 30 and 35? 30. And we, all right. 35 and 38? Okay. And increment left. 38 and 45? 38. And we increment the right. 48 and 45? 45. And then we still increment. We still increment. Which you happen to know is past the length. So since it's past the length, what do we do? Yeah, then you usually what you're going to want to do is write one loop that just compares it until one of them is past the length, and then just write a quick code that which one's ever not past the length, just add them all in. That's the way I would do it. So then you get that 48 in there, and then 62, and now it's 4 over here. Is this list sorted?
Yeah.
Yeah. So it merged. This is the merge operation. All right. Perfect. Okay. I think we went over it. Let's go through it with the slides just to make sure it's in everyone's brain. If the list is the size greater than 1, okay, that's your base case. The size is 1, return, you're done. If it's greater than 1, divide the list into 2 sublists, so you have to have at least 2 elements, so of course you're going to have at least 1 element in each sublist. Merge sort the first, merge sort the second, aka recurse on yourself. First on the left, then on the right. Of course you could do the right first and the left, it really actually does not matter the order here. But you must do the 2 merges, merge sort recursive calls before you do the merge, the first list and the second list. Okay? Simple enough. Hey, what data structure is this?
Linked list.
So I did up on the board with an array, which works just fine. This actually works fairly well with the linked list as well. In actuality, how hard do you think quicksort would be to do with the linked list?
Not very.
Not too hard, but it's going to be, there'd be a lot of pointer jumping around.
Yeah,
But you're going to
I wanna
see
do it.
here, since you're just straight up merging lists, it's actually not that bad. So divide, head and middle, you're really just moving the 2 pointers over until the middle is about halfway in. And then you have the head going to the middle here, and then the other head going to the next one. Where we go? Wow, it's gonna skip a bit, brother. Wow. All right. The idea is that what you'd want to do is probably set this middle to null. So now you literally have 2 lists, the other head and the first head. Knowing that that ends in null, you call the merge sort again on the 2 lists, because you've already null terminated one list, right? By making something in the middle go null, you've made the 2 lists essentially. You have the first head and then the second head. Then you would call merge sort. You would recurse a lot, but let's go ahead and look at the general case where you see the 2. Since you know you got to merge these 2, remember the merge sort's been called. We're just going to say that it's merged everything. I just want to show you what the general section of merging 2 lists is going to be, because it's actually fairly straightforward. You start at the beginning. You have your 2 rovers, and you compare the first element, 18 and 25. Well, the 18's first. So that would start your new list, and you increment the first rover. to the 25 or the 20, and then you continue on moving it like that. Yeah, so here we go. Last merge start here, your new head first over here. Noticing that the 20 is less than, the 18 would then go to the 20. First is over at 30, the other first is up here. Wow. Next, you would have the 20 go up to 25, incrementing first. Then the 25 would go to 30, 30 to 65, 65 to 45, then to 75, then back up to 85 and 95. Everyone okay with that? All right. All right, merge sort. What do you think merge sort is? In big O analysis of, let's see, comparisons. Where are comparisons being done?
Just end.
On this picture, where are comparisons being done? Orange or blue?
Blue.
Blue, yeah, there's no comparisons in the orange. The orange is just setting up recursive calls. That's all it's doing. So really, you're just doing the comparisons of the merge. At each level, how many comparisons are done? O of n. You're doing n comparisons. And how many levels are there? 3. 3. If there's 3 levels and 8 variable, and 8, the length is 8. Oh, what's 2 to the third? 8. 8. There's 16. Then there would be 4 levels here as well. So this is, hopefully you can see by the fact that it's dividing everything in half. The lists, every time you're doing a list, actually kind of doing the inverse here, combining 2 halves. Again, that's a log n number of levels or steps here. I know it's kind of some hand waving here. It'll make more sense in algorithms, but we got to get big O analysis in everyone's head. So each step is O of n. Each level is O of n, and they're log n levels. So what's the total algorithm? N log n. Yeah. Okay, let's see how they do it. So you have n elements. Suppose that n is a power of 2, n equals n to the m, so just for sake of argument. So m would be the number of recursive calls. Well, since it's 2 to the m, aka number of recursive calls, all right, they're going through and showing you that, hey, look, when you divide it by 2, you're really helping, you're really showing that it is log n. To merge 2 sorted lists requires s plus t minus 1 comparisons, basically O of n comparisons. So the max number of comparisons at level k is O of n. That's what I was trying to point out earlier. Maximum number of comparisons each level is O of n. Maximum number of comparisons in m, where m is the number of levels of recursion. Well, we already showed you that the number of recursions is about log base 2 of n. So average case is n log n, and even the worst case is still n log n. Because there's no real worst case here. You're just dividing it by 2 and then merging. You can't. The algorithm really doesn't get worse or better. It just behaves in a very concrete fashion. All right. Are there any questions on quick sort or merge? First off, any questions on merge sort? One thing I want to show you, and this is very subtle when I was talking on the board, but when you go to code this, it's a little trickier. If you have 2 arrays and then you want to merge them into a 3rd array, you're going to need to allocate memory for a 3rd array for the merge. All right? What that means is merge sort for an array, while it guarantees n log n, it requires 2 times n memory. See, quick sort, it sorted, actually bubble sort, selection sort, insertion sort, and quick sort are all called in-place algorithms because they sorted everything in the array, did not require any extra memory. Merge sort, when using an array, uses twice the amount of memory because you need to buffer the new list when you go and you merge it, okay? Just keep that in mind when you go up to code that. It's not, if you keep that in mind, it's not that big of a deal. You just need to code it up. I recommend that when merge sort starts, just create a new array, same size, and just use that array to store all your variables.
Would you reuse that array?
Yeah, I'd reuse that array until the whole merge sort was done, and then I would deallocate. That's the way I would do it. All right, any questions about quick sort or merge sort? Can y'all tell that these two are going to be significantly faster than bubble selection or insertion? All right, good, because you'll be creating a graph to show that, and it should pop out pretty quickly.